Good morning, class. You guys have made it to the last section of notes for Calc 3. This is the divergence theorem. It goes with flux. So remember how we had Green's theorem and we had the tangent, which was circulation, and normal, which was flux? Well, then Stokes' theorem was like split into two. We did Stokes' theorem, which we use for circulation. We use the divergence theorem, though, for flux. So what is the divergence again? We'll recap what that is. We did this in the Green's theorem section as well. Again, it's just the gradient dotted with the field, and it's the rate at which the fluid is being piped in or drained away at that point. Okay. Again, as I'm going, please pause the screen to write things down, because I'm on a time limit here, so I'm going to keep going. So the divergence, find the divergence of this field here given. So again, the only thing we have to look for is we need to dot the derivative or the gradient with the field. And what that means is for the x or the I component, we're going to take the derivative of that with respect to, it would help if my pen worked. We're going to take the derivative of the first piece with respect to x. So if I do that, and if my pen would work, we can get this done. Hopefully you guys see that if you take the derivative of 2xz with respect to x, you're going to get the point 2z, and then plus you take this with respect to y and you get a negative x, plus you take this with respect to z and you get negative 1. So the answer to this, or the divergence of f, is just 2z minus x minus 1. And that's it. Okay? Alright, so now this is the divergence theorem, which is basically the flux version of Stokes' theorem in a way. Where circulation was for Stokes, this is for flux. So the flux of a vector across a closed oriented surface in the direction of the surface's outward unit normal field n equals the integral of the divergence over the region enclosed by the surface. So what we're basically doing is we're turning the flux integral into a triple integral of divergence, and those are the same thing. And sometimes it's way easier to do that. So again, here you can pause the screen here to get everything, and then I will be moving on. So the second problem, or second example on this next page, says evaluate both sides of that equation I just wrote down. Okay. Well, first thing we need to do is find the normal vector, and remember, flux is the normal vector of the surface. So here's my surface. So again, n is the unit vector of the gradient of f. So we know that the gradient of f is just the partial derivatives. So it's 2x, 2y, 2z. Sorry. So we know, and by the way, this is one of the sides. And then we know that the magnitude of that is 4x squared of 4x squared, 4z squared. Okay, you can simplify this now and say that the actual normal vector is the vector 2x, 2y, 2z over the magnitude. Well, I can simplify this magnitude. I can pull a 4 out, and that becomes a 2 out here, and I'm left with just the square root of x squared plus y squared plus z squared. So if I'm looking at that, luckily for that sphere, it's defined that x squared plus y squared plus z squared equals a squared. So this just becomes a. So that means that the normal vector is just x, y, z over a. Okay. Now we have to do f dot n. So I'm taking this and dotting it with this. So if you do f dot n d sigma, well, first we're going to do f dot n. We get this times this, so we get x squared plus y squared plus z squared over a. Again, x squared plus y squared plus z squared is equal to a squared, so we just get an a. So f dot n is just a. So now we can say that the flux is equal to the double integral over the surface of a d sigma. Well, since A is a constant, we are just talking about A times the surface area of this sphere. And I know you guys might not remember your geometry. A surface area of a sphere is 4 pi r squared. It actually also happens to be the derivative of the volume of a sphere. So this is 4 pi, and then instead of r though, it's a, so a squared. So we get that the flux is 4 pi a cubed. Alright, now let's try it using the other new method without doing all this crazy work. This is how easy the divergence theorem is. You find out what the divergence is. So if we go to the field is x, derivative of x with x is 1, plus derivative of y with respect to y is 1, plus the derivative of z with respect to z is 1. So the divergence is 3. So the flux is also equal to the triple integral over the domain of this formula, the divergence, and then the volume over that region. Well, we already just did this number. That's a 3. So we get 3 times the volume of that surface, which is a sphere. Do you guys remember the sphere equation? It is 4/3 pi r cubed. Again, r is a. And sure enough, what happens when you multiply 3 and 4/3? We're left with 4 pi a cubed. And there is showing that that formula matches. And it's much easier. I think this is one of my favorite ones, because the dot product just gives you, something a lot nicer. So let's do one more, because I have time, and then I will stop after example 3. Tomorrow we'll do example 4 and recap, and then you guys will just be given some work problems to do for the rest of the week or so, and a little bit into the next week. So, alright, find the flux outward through the surface. So again, normally with flux, if it's a cube, you'd have to actually do separate integrals for each surface, so we don't have to do that. So instead of doing 6, we can just do the divergence. So the divergence of this field, excuse me, this with respect to x is y, this with respect to y is z, and remember when you do a dot product, you're adding, and then x, so that's what we got. So the flux will be set up as the triple integral. Since it's a cube cut in the first octant by the planes x equals 1, y equals 1, z equals 1, that means that each bound is 0 to 1 for x, y, and z. My divergence we found was this, so we're going to just put that right here. I'm just going to put it x plus y plus z, and then it's dx, dy, dz. So that is the setup for this problem. This is the flux problem. So let's integrate and see what we get. So the flux is equal to, we get x squared plus xy plus xz, evaluated from 0 to 1. Still the double integral. Alright. Put 1 in for x. You get 1 plus y plus z. So 1 plus y. Wait, that's not correct. I screwed something up. This should be a 1/2. Excuse me. 1/2 x squared. That's one of those days, everyone. 1/2 x squared plus xy plus xz. Now I get, when you plug a 1 in, you get the 1/2 plus the y plus the z, dy dz. You'll actually start seeing a pattern for this problem because it's the way it is. So now we get 1/2 y when I integrate with respect to y, plus 1/2 y squared plus zy. So we put a 1 in for y, and we get 1/2 plus 1/2, which is 1, plus z. So we get 1 plus z dz. We're going to integrate that from 0 to 1. We do it one more time, and we get z plus 1/2 z squared. From 0 to 1, 1 plus 1/2 is 3/2. So the flux of that field outward through the surface of the cube is 3/2. Okay, I'm going to stop there for today, and then, like I said, we'll finish up the notes and maybe start with problems tomorrow. But that is the divergence and flux. I'll see you guys next time.